we have already talked about all those building blocks of the neural network. So we have all the pieces together, but we didn't talk about a very critical, very important and essential part of neural network programming, which is the training process. So in this training process, it's not just particular of neural networks. Any machine learning model, any even regression model has to go through a training process. The training process basically consists of taking your model and your training data and using that training data to make your model fit to that training data. So when your model is fit to that training data, it learns from that training data, then the model becomes capable of doing accurate predictions. So that's why the training process is essential. It basically makes your model useful. So in a typical linear regression model, you just do one pass through the data. Like you initialize random weights or slopes, and then you calculate the errors given those weights, the errors relative to the ground truth observations. So you see how wrong your model is utilizing those weights, and then you try to optimize those weights to update their values and make the model more accurate. So that's the typical fitting process in any machine learning model, right? In neural networks, it's more like an iterative cycle, iterative set of steps where you pass through the data multiple times, doing all those steps, updating the weights, and then you calculate again the loss or how wrong the model is based on those updated weights. And then it passes through the data again, updating those weights again, and it keeps going, updating the weights over and over until the model converges, which means when the model finds a solution that is the best set of weights that returns the best accuracy and cannot improve anymore, no matter how additional steps you keep adding, you can't find anything better than those specific weights, and you get stuck in that best optimal solution. So this cycle in neural networks keeps going over and over. So at step 1, it starts with random weights, and then it goes through step 2, 3, 4, and then it gets back to step 2 and keeps going in this cycle. And usually we work with massive amounts of data in AI, but we don't update the weights after seeing the whole data. We can split the data into smaller batches and batches of a smaller number of samples. Let's say if we have 100 samples, we split that in 10 batches of 10 samples. After seeing that first batch of 10 samples, you can already go and update the weights, and then you make the model go through the next batch, update the weights again, go through the next batch, update the weights again. So that batch training is very typical in AI. And a batch is usually how many samples are processed before updating the weights. If you set a batch size that is too small, it will be very easy to parallelize your code, to distribute the code throughout the GPUs. It will be very fast to update the weights for one batch, but you may see more fluctuations because that's such a tiny batch may not be a real representation of the whole population. So if you have many variations in your training data, you may see too much fluctuations if you use a very tiny batch, like a batch of one sample that's too small. And if you use a batch that is too large, you just do a few passes on the data, you do just a few updates, you see less fluctuations, but you may run into a few computational issues. If your batch is too large, it may not even fit into the memory of the GPU, and you may not leverage the GPU acceleration power as much as you would if you use a little bit smaller batch size. So those are things that you have to take into account when you are preparing your data for training your neural network and for using the GPUs. There is no standardized convention. Oh, this batch size is the perfect for every problem, for every situation, for every GPU. There's no such thing like that. A lot goes from trial and error. There is a range of batch sizes that are recommended. Like I see many people using 32 samples per batch, 100 samples per batch, and so forth, even 252, etc. Sometimes you use a multiplier in 8 bits size. That's why you see 16, 32, etc. But there's really no sweet spot for every type of problem. You have to do some experimentation and see what is the batch size that fits better to your data, that gives a better accuracy and a faster training speed in the end. And just another terminology is the epoch. When you see that a lot when you train your neural networks, an epoch is basically one pass through all the batches. So when the model finishes going through all the batches one time, updating the weights one time, so one pass of step 2, 3, and 4 throughout all the samples, all the batches, then that's one epoch. So usually when you see tutorials online or guides, materials, and say, oh, the model was trained for 100 epochs, it means that you did step 2, 3, and 4 throughout all batches 100 times. So that's basically what it means. And you also gonna see another concept, which is the gradient descent. That is a very essential part when training an artificial neural network. I'm not go deep into the math of doing those calculations right now, but when you see your implementation, we're gonna go through some practical, some hands-on examples. You're gonna have to choose what optimizer you want to use for training your model, which is basically what type of method or algorithm it's gonna use for doing those training cycles. In that loop, that cycle of steps here that I mentioned before is usually called a gradient descent. When you calculate the loss given the current weights, and then you compute the gradients and you update the weights, you basically, in the first cycle, you are starting with a certain model weight value that gives you a certain loss value. So I have an example here representing the weights versus the loss. And the optimizer basically does an optimization process through this gradient descent technique, where it tries to adjust the weights so that the loss, the amount of error of the model, minimizes. So if you imagine this valley, you start your model like dropping a blind model into this valley, and you tell the model, go downhill. So the model is blind, it's trying to do random steps, and then these random steps, they are optimized to try to go downhill, to try to minimize the error. And updating the weights so that they minimize the error is basically what this gradient descent algorithm does. It's the optimizer steps, part of the optimization steps. Whenever you have to train your model, you have to specify what kind of optimizer you want to use.